Today we want to talk about Chapter 8, Part 2, Concepts of Chemical Bonding. Now, a chemical bond formed by sharing a pair of electrons is a covalent bond, and the hydrogen molecule H2 provides the simplest example of a covalent bond. Now, when two hydrogen atoms are close to each other, the two positively charged nuclei repel each other, as you can see here. The two negatively charged electrons repel each other, as you can see here, and the nuclei and electrons are attracted to each other. As you can see in this figure, now because the molecule is stable, we know that the attractive forces must overcome the repulsive ones. Now, thus the atoms of hydrogen molecule are held together principally because the two positive nuclei are attracted to the concentration of negative charge between them. In essence, the shared pair of electrons in any covalent bond acts as a kind of a glue to bind atoms together. So again, there are several electrostatic interactions in these bonds, attractions between electrons and the nuclei, repulsion between electrons, and repulsion between nuclei. And in this figure, you see here the attractions and repulsions among electrons and nuclei in the hydrogen molecule. And down here, we see electron distribution in the H2 molecule. Now, let's move to the so-called Lewis structures. Now, the information of covalent bonds can be represented with Lewis symbols. The formation of the H2 molecule from two hydrogen atoms, for example, can be represented as this. In forming the covalent bond, each hydrogen atom acquires a second electron, achieving the stable two-electron noble gas configuration of helium. Now, another example, formation of a covalent bond between two Cl atoms to give Cl2 molecule can be represented in a similar way, as you can see here, by sharing the bonding electron pair. Each chlorine atom has 8 electrons and octet in its valence shell, thus achieving the noble gas electron configuration of argon. Now, the structures shown here for H2 and Cl2 are called either Lewis structures or Lewis electron dot structures. Now, in writing Lewis structures, we usually show each shared electron pair as a line here, as a line, and any unshared electron pairs as dots. So we have shared electrons, unshared electrons, as you can see here. Now, for nonmetals, the number of valence electrons in a neutral atom is the same as the group number. Therefore, one might predict that 7A elements such as fluorine would form one covalent bond to achieve an octet. 6A elements such as oxygen would form two covalent bonds. 5A elements such as nitrogen would form 3, and 4A elements such as carbon would form 4. Then fluorine form 1, oxygen form 2, nitrogen form 3, and carbon forms 4, as you can see here. Now, in this sample exercise, Lewis structure of a compound, predict the formula of the binary compound formed when nitrogen reacts with fluorine and draw its Lewis structure. This is nitrogen, group 5, it has 5 valence electrons, plus fluorine, group 7A, 7 valence electrons. So we need 3 of the fluorines in order to bind to one nitrogen, as you can see here. And this is the final Lewis structure. This is the Lewis structure. Now, multiple bonds. First double bond. In carbon dioxide, bonding occurs between carbon and oxygen as follows. Again, oxygen, 6 valence electrons, carbon 4. So we need 2 of these oxygen to form. So in carbon dioxide, for example, bonding occurs between carbon with 4 valence electrons and oxygen with 6. Carbon requires an octet by sharing 2 electron pairs with each of the 2 oxygen atoms. Each double bond involves 4 electrons. However, a triple bond corresponds to the sharing of 3 pairs of electrons, such as in the N2 molecule, as you can see here. Now, because each nitrogen atom has 5 valence electrons, 3 electron pairs must be shared to achieve the octet configuration. Now, the properties of nitrogen are in complete accord with its Lewis structure. Nitrogen is a diatomic molecule and it's gas with the exceptionally low reactivity that results from the very stable nitrogen-nitrogen bond. Now, the nitrogen atoms are separated by 1.10 angstrom. The short separation distance between the 2 nitrogen atoms is a result of the triple bond between the atoms. So, as a general rule, the length of a bond between 2 atoms decreases as the number of shared electron pairs increases. So here we have single bond is longer than double bond, and the double bond is longer than triple bond. But which one is the strongest? Of course, it is the triple bond. We come to the so-called bond polarity and electronegativity. Now, when 2 identical atoms bond, as in Cl2 or H2, the electron pairs must be shared equally. When 2 atoms from opposite sides of periodic table bond, such as NaCl, there is relatively little sharing of electrons, which means that NaCl is best described as composed of Na plus and Cl minus ions. The 3s electron of the sodium atom is in effect transferred completely to chlorine. The bonds that are formed in most substances fall somewhere between these extremes. Now, bond polarity is a measure of how equally or unequally the electrons in any covalent bond are shared. For example, a nonpolar covalent bond is one in which the electrons are shared equally, like in Cl2 or F2 or N2. In a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other. Now, electronegativity is defined as the ability of an atom in a molecule to attract electrons to itself. And the greater is the atom's electronegativity, the greater its ability to attract electrons to itself. It is related to the atom's ionization energy and electron affinity. Now, if we look at this figure, it shows us the electronegativity values for elements in the periodic table. What is the general trend in electronegativity? Notice that electronegativity increases from left to right in the periodic table and decreases from top to bottom. So you should know this. And then again, on the periodic chart, electronegativity increases as you go from left to right in across a row and from bottom to the top of a column. So you should know these trends in electronegativity. Now, electronegativity and bond polarity. Electron density distribution. Though atoms often form compounds by sharing electrons, the electrons are not always shared equally. Fluorine pulls harder on the electrons it shares with hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than hydrogen, as you can see here. So we can say this is unequal sharing, whereas in F2 it is equal sharing. So this is a computer-generated rendering, shows the calculated electron density distribution on the surface of these two molecules. Now, electronegativity is important, as we will see in determining whether a bond is polar or not. So that the greater the difference in electronegativity between two atoms, the more polar their bond. Okay, now we come to a concept called dipole moments. Now the difference in electronegativity between a hydrogen and fluorine leads to a polar covalent bond in the HF molecule. As a consequence, there is a concentration of negative charge on the more electronegative fluorine atom, leaving the less electronegative hydrogen atom at positive charge here. Now, a molecule such as HF, in which the centers of positive and negative charge do not coincide, is a polar molecule. Thus, we describe both bonds and entire molecules as being polar and nonpolar. And we can indicate the polarity of each molecule in this way. We can draw an arrow from left to right. So when two atoms share electrons unequally, a bond dipole results. So polarity helps determine many properties. Polar molecules are likewise attracted to ions. Now, how can we quantify the polarity of a molecule? Whenever two electrical charges of equal magnitude but opposite sign are separated by a distance, a dipole is established. Now, the quantitative measure of the magnitude of a dipole is called the dipole moment, denoted mu, produced by two equal but opposite charges separated by a distance r, and is calculated by this law, mu equal qr. Now, this expression tells us that dipole moment increases as the magnitude of q increases and as r increases. For a nonpolar molecule such as F2, the dipole moment is 0 because there is no charge separation. Now, dipole moments are usually reported in dBi. dBi is a unit that equals 3.34 times 10 to the minus 30 coulomb meter. For molecules, we usually measure charge in units of electronic charge, and that's equal for one electron, the charge of one electron, 1.60 times 10 to the minus 19 coulomb, and distance in angstrom. This means that we need to convert units whenever we want to report a dipole moment in dBi. So measurement of the dipole moments can provide us with valuable information about the charge distribution in a molecule, as it is illustrated in sample exercise 8.5. Now, the bond length in the HCl molecule is 1.27 angstrom. Calculate the dipole moment in dBis that would result if the charges on the H and Cl atoms were +1 and -1 respectively. So let's start with this part. لاحظوا, the charge on each atom is the electronic charge, as I said, E equal 1.60 times 10 to the minus 19 coulomb. The separation is 1.27 angstrom. So the dipole moment, mu, can be calculated in this way. It's equal 6.08 dBi. Now, this is if the charges are +1 and -1, but the experimentally measured dipole moment of HCl is only 1.08 dBi. What magnitude of charge in units of electron on the H and Cl atoms would lead to this dipole moment? So, we know the value of mu and the value of R. Again, we want to calculate the value of Q. So Q equal mu divided by R, you see, and this is Q. Now we can readily convert this charge to units of electron, and this equal this value. So thus the experimental dipole moment indicates that the charge separation in the HCl molecule is HCl bond is polar covalent rather than ionic. So here, so the partial positive is 0.178 and the partial negative, which is equal to 0.78. So we conclude that HCl bond is polar covalent rather than ionic. Now this table, however, shows us bond lengths, electronegativity difference, and dipole moment of hydrogen halides in general. So we have here HF, HCl, HBr, HI. لاحظوا halides of group 7A. This is the bond length of each one in units of angstrom. Now, this is the electronegativity difference, and this is the value of dipole moment, as you can see here. Now, notice that as we proceed from HF to HI, the electronegativity difference will decreases and the bond length increases. Now, the first effect decreases the amount of charge separated and causes the dipole moment to decrease from HF to HI, even though the bond length is increasing. Calculations identical to those used in sample exercise 8.5 show that the charges on the atoms decrease from plus 0.41 and minus 0.41 in HF to plus 0.057 and 0.057 in HI. So we can visualize the varying degrees of electronic charge effect, the electronic charge shift in these substances from computer generated, etc. So for these molecules, the change in electronegativity difference has a greater effect on the dipole moment than does the change in bond length. So again here, the greater the difference in electronegativity, the more polar is the bond. So which one of these four polar covalent bond is the most polar? Of course, it is HF. Why? Because it has greater difference in electronegativity. Remember this. So again, this shows us charge separation in the hydrogen halides. In HF here, the strongly electronegative fluorine pulls much of the electron density away from hydrogen. Now in HI, the I being much less electronegative than F does not attract the shared electrons as strongly, and consequently there is far less polarization to the bond. End of part 2 in chapter 8.